Hello, this is Mrs. Jones and welcome to my lesson on keeping warm, and we're going to be looking at energy being transferred by heating mainly. So what I'd like you to do is see if you can remember first of all the names of the three ways that energy can be transferred by heating that you might have learnt about in your Year 8 lessons. You can use the pictures as clues. If you can describe those methods that you learnt about in Year 8, that's even better. You can also have a think about the challenge question of does cold exist? Okay, so you might have remembered from Year 8 the names of the different methods of heat energy transfer as conduction, convection and radiation. You should have done a couple of lessons on this. And you might have been able to describe a little bit about how conduction, convection and radiation transfer energy by heating, but we'll be looking at it during this lesson. And if you had to think about the challenge question, it was, does cold exist? Well, Einstein says no, and it's actually just the absence of heat energy being, or thermal energy being stored within a material in its particles. Temperature of a material is a direct measurement of the kinetic energy of particles. So how much motion do those particles have? If the object is a solid, then the particles will just vibrate. If they are a liquid or a gas, then the particles will have a velocity, they will have a speed. So you can measure that and you can work out the kinetic energy of those particles, and that is directly related to the temperature that the material will read and will measure at. If something feels cold, it's relative, it's cold compared to you. So if you touch something and it feels cold, it means that the heat energy is being removed and conducted away from your skin. And things that are very good at conducting heat energy, or good thermal conductors, will remove heat energy much more quickly and they will feel colder to you. So during this lesson we're going to be having a look at the three methods of heat energy transfer and having a look at this idea of thermal conductivity. We're going to be seeing what affects the rate of heat energy transfer through a material, and also have a look at ways of reducing energy transfers and how homes can be made more efficient. And you may have seen this animation before. Like I said, in your Year 8 lesson you might have seen this. And conduction only happens in solids, and that is because the particles are vibrating in solid materials. They're not moving around each other like they are in liquids and gases, so they can just vibrate in place. But when a solid particles heat up, they start to vibrate more, and those vibrations are passed on from particle to particle. The particles can't move around each other, they can just sort of vibrate in place. So they vibrate more than they were before, and they pass on that energy to the neighbouring particles. And you can see in this animation that as one end of the solid is being heated up, that its particles start to vibrate more, and those vibrations gradually get passed on to the next particle and to the next particle until the whole object has become a higher temperature and the heat energy is transferred from one end to another. Saying here that metals are good thermal conductors. Metals are very, very good at transferring energy by heating in this way, and we say that they have high thermal conductivity, whereas insulators are low thermal conductors and they don't pass on heat energy from one end to another very quickly. They still do, but just not as quick, so we say that they are poor conductors. Okay, so moving on to convection. There's a nice animation here, again one that you may have seen in a previous lesson, and convection happens in liquids and gases. So in physics we refer to liquids and gases as fluids sometimes because the particles can move around each other, and so we say that they're fluid. They can be poured. Just thinking about pouring a glass of water into another glass. It can also happen with gases, but you can't necessarily see that happening. So we say that liquids and gases are both fluids. And with convection, there's a little bit more to explain because it's actually to do with density, which is something you don't really learn about in detail until Year 11. But in terms of the way that convection actually works, it's to do with the density of the material that we're looking at. So here we're just imagining heating a pan of water on a stove, or using a Bunsen burner to heat a beaker of water. Where the heat is being applied it's going to transfer the energy first of all by conduction through the solid material, but then to the fluid in there. So in this case it's water, and the bit of water that's closest to the heat source will gain energy. It will increase particle motion, i.e. the particles will gain speed, and they will actually start to take up more space and become less dense, which means there are less particles in a fixed area. But again, you'll learn more about that in year 11. When the particles are less dense than the other particles around it, they will rise above it. So it's almost like becoming lighter, but not, because it's to do with the density and not the weight of it. So the less dense fluid will rise up and the more dense fluid will fall down and take its place. But when it does that, the more dense fluid takes its place and actually takes a position closer to the heat source, and then in turn gains heat energy. It heats up, the temperature rises, it reduces in density and then rises up. So what you end up with is a cycle of the material getting hotter, rising up, then getting cooler and falling back down again. The reason why it gets cooler is because it moves away from the heat source. So when it gets to the top and it's not near the heat anymore, it cools down and then it falls back toward the heat source. So this cycle is called a convection current, and it happens in liquids and gases. Radiation is a little bit different because it doesn't involve particles necessarily, although radiation can travel through materials and it can also travel in a vacuum. So a vacuum is a place where there aren't any particles like in space. So radiation is a little bit different because it doesn't need particles to transfer heat energy from one place to another, because it actually transfers heat energy through a wave or electromagnetic radiation. There's a little diagram here of the electromagnetic spectrum, which you'll learn a little bit more about in topic 5. There's the visible light, which is the light that we can see with our eyes, but there's also a portion of the electromagnetic spectrum called infrared radiation, which we can detect with our skin and with our bodies, that feels warm or feels warmer. So when infrared is being emitted, we can say that it is transferring energy by heating, but it's by radiation rather than by particles like conduction and convection. And we talked about that in the previous lesson when we looked at energy being transferred by heating. So infrared radiation or radiation is a little bit different because it doesn't need particles to travel, and it travels from one place to another in the form of a wave rather than using particles. What I'd like you to do is have a go at making some notes on conduction, convection and radiation. The best way to do this is to look at these animations and use these keywords that I've put. So I've got a few here for conduction and quite a few more here for convection, and then some for radiation as well. And the best way to do this is to just think about what you've learnt, look at the animations and write in your own words a little description of each: conduction, convection and radiation. If you need to, you can always rewind the video and have a look at the slides on conduction, convection and radiation as well if you need a little bit of extra help. And also, once you've done that, I'd like you to try to write a definition in your own words for thermal conductivity. Okay, so hopefully you've got some good notes on conduction, convection and radiation, and if you had a go at writing a definition for thermal conductivity, compare it to what we've got here. So thermal conductivity is a measure of a material's ability to conduct energy by heating, so how well the material conducts energy by heating. The higher the thermal conductivity, the more easily heat energy will conduct through it or pass through it. So make sure you've got something similar to this and you've got a definition written down for thermal conductivity. Then what I'd like you to do is have a look at this data. The data shows the thermal conductivities of some different materials here, and they're put in order from highest thermal conductivity to lowest thermal conductivity. Don't worry about the units because you don't really need to know that, but what I want you to do is have a look at that, pause the video and try and answer these 3 questions. Then once you've done that, unpause the video and come back for the answers. Okay, so hopefully you've paused the video and had a go at answering the questions. So for question 1, which substance is the best conductor? And the answer is diamond because it's got the highest thermal conductivity, and they're quite conveniently put in order here. Compare the thermal conductivities for copper and iron. Well, if you have a look, copper here is 400 and iron is 80. So the answer to that is simply that copper has a higher thermal conductivity than iron. And then for the last one, why do you think air's got such a low thermal conductivity? You can see it's right here at the bottom. And the answer to that is, first of all, it's a gas, and gases have low density, and that will make it a poor conductor, because conduction only really happens in solid. So the fact that air is a gas and has such low density means that it's not very good at conducting. Helium is also a gas, but the particles of helium are lighter than the particles that make up air. So what that means is when heat energy is passing through helium, the particles can travel more quickly and pass on the heat energy from one place to another a bit more quickly. So even though helium is a gas, it's got a higher thermal conductivity, even though thermal conductivity is still quite low. Okay, so what you can do now is have a look at these 9 situations and see if you can work out if they are examples of conduction, convection or radiation. There are a few in here that we haven't learnt about in detail yet, so see if you can work them out. Okay, so hopefully you've had a chance to pause the video and see if you can work these ones out. So number 1, metal part of your seatbelt burns your leg, is conduction. Accidentally touching a hot stove is also conduction. Heating a pan of water is done by convection. Walking across hot sand burns your feet is conduction. Getting a tan or getting sunburn is caused by radiation, which is ultraviolet radiation that causes that. This kind occurs more quickly with darker objects. Well, we haven't really learnt about this yet, but what we'll learn about in future is that darker objects radiate and absorb radiation much more quickly than lighter objects. Number 7, causes the wind on Earth is convection, because when air gets hot it rises and cold air rushes in to take its place. Metal spoon in a soup heats up is by conduction, and a flame burning something is actually caused by radiation. Okay, so now we've had a look at conduction, convection, radiation and thermal conductivity, we're going to have a look at how that actually applies to some real life situations. And what you can do is you can have a look at this diagram of a house, and it's got some bits of information around it telling you about ways that it might make the house or the people that live there and the home a bit more energy efficient, maybe save them a bit of money. And what I would like you to do is just have a look at this and make some notes on the different things that homes can do to be more energy efficient, and think about which ones of these actually apply to heat energy transfer. So there are a few different things here. Some of them are to do with reducing energy transfer by heating, and some of them are just to do with using less energy. So for example, low energy light bulbs. It means that you're going to be using less energy. Having appliances switched off and not on standby uses less energy. Recycling means that less energy will be used overall, because it takes more energy to do something from scratch than it does to recycle, as far as we are told. Solar panels as well, not really reducing energy transfer, but actually using radiation to produce electricity instead of using electricity from the national grid. So solar panels tend to be more environmentally friendly because we're using a renewable energy resource. But the other things on here are to do with reducing energy transfer by heating. So the obvious ones are the insulating materials. So double glazing is an insulator because the glass traps a layer of air, and we know that air is a poor conductor, so it reduces conduction through the windows because you're trapping a layer of air. And some double glazing actually even has a vacuum in there, so you've not got any particles in there for conduction, convection to happen. Similar cavity wall insulation and loft insulation, they work in the same way. The materials have low thermal conductivity, so they don't transfer energy through them very quickly, but they also trap air. So cavity wall is like a foam that gets sprayed in, then it sets and it traps air. So similar to double glazing, air being a poor conductor. Loft insulation, sometimes made out of fiberglass, it's got low thermal conductivity, and it also traps layers of air in there which don't allow heat energy to pass through very easily. Same with the foam jacket around the boiler in this example. It's an insulating jacket that goes around the hot water tank to try and stop the energy just transferring out of the hot water tank and keeping it within the hot water. This one here about having the thermostat set low is to do with the temperature difference between the inside and the outside. If there's a really big difference between the temperature inside and outside, then you'll get lots of energy transferring from the hotter place to the colder place, or energy transferring at a faster rate, should I say. If you set the thermostat low, it means the temperature difference isn't as much, so it's a more similar temperature inside and outside, so you get less energy transferring in a certain amount of time from the inside to the outside, so the rate of energy transfer is less if the temperature difference between the two is less. So the main ideas really are reducing energy transfer by heating for those different reasons, the thermal conductivity, reducing conduction and convection, and also lowering the rate of energy transfer from the inside of the house to the outside of the house. So pause the video and see if you can have a go at these two questions. If you get the first one, then you'll be able to work out the second one quite easily. So just pause the video and see if you can write down the 3 things that affect the rate that energy is transferred through a material by heating and how we could actually go about reducing those. Okay, so hopefully you've had time to have a think about that and make some notes on it. 3 things then that affect the rate of energy transfer across the material is first of all the thermal conductivity. So if you've got high thermal conductivity, you'll get a faster rate of transfer. Thickness of the material. If the material is thicker, then it is going to mean that it's more insulating and it's going to reduce the rate of energy transfer. And then the last one is the temperature difference. So the bigger the temperature difference between one side of the material and the other, the faster the rate of energy transfer will be. So how could we reduce the rate of energy transfer? Relating them directly, we can decrease the thermal conductivity or choose materials that have a low thermal conductivity for insulating. We can have materials that are very thick, so increase the thickness, and then also decreasing the temperature difference across the material will help to keep energy in and stop it transferring to the outside very quickly. Okay, so here's an activity for you to be getting on with. What I want you to do is have a look at this diagram here of the house and the features that have been included when building this house, and explain how each of those features helps to make the house more energy efficient. There's a challenge activity here as well, and it's showing a picture diagram of a house that is built in a hotter climate. And for the challenge activity, you can explain how each of these labelled features helps to actually keep the house cool in a hotter climate, and how that might help to save the person who lives there some money. Okay, so here are the answers to the task, looking at the different ways that the house was built and designed to improve the energy efficiency and stop energy being transferred by heating. So what you can do is, rather than me talking through it, just pause the video, have a look what you've written down, and have a look what's here, and then add anything that you've missed to your notes. Okay, so that brings me to the end of a lesson on keeping warm and energy transferred by heating. And you might want to have a look at this infrared image of a house and think about what advice you might give to the people who live in this house that might help them save some money and improve their energy efficiency. Thanks for watching.